Yeah, we kind of got a little sidetracked there. Sorry, but how do sharks fit in? Sharks, I mean, Sharknado. That's might have a Sharknado on a tectonic interface. But as far as the median Earth temperature lab, talked about the siting, the installation, and now this week we're looking at the actual implementation. Here would be your information on that. Week 5 median temperature lab. Hopefully you have your temperature sensors set and you can start your daily data logs, USB or manual recording. Remember to record your underground temperature twice daily at least 8 hours apart. A total of 28 readings, preferably over a 3-week period starting 9/30/15 to roughly 10/31/15. And we'll see, if it's not getting done, don't worry, we can stretch that out. As the temperatures get colder, the earth or the air temperatures get colder, it's actually a more effective experiment, as long as the depth temperature or the 72-inch sensor is well insulated. Remember too that you need a sensor on the surface, and the sensor that's on the surface, it's important that it's sheltered, that it doesn't have the sun shining on it, and that it's not getting rained on and that kind of stuff, so you don't have evaporative or bulb. Type of vegetation or the shelter building surrounding your surface temperature sensor. Specific location of the underground temperature sensor, example, capped well. This is the data that you'd like to include in your experiment information section. And then the surface sensor must be protected from sunlight. Now also, the aspect of your site is important. Which way does the slope? Is it a steep slope? Hopefully 0 to 20 degrees. Not, if it's more than 20 degrees, stuff's going to be rolling off. But and if it's facing north, then you're probably going to have a little different result than if it's facing south, because of angle of incidence or insolation. How the sun hits the surface of the earth. What I don't want you to start thinking is that the sun has much to do with median temperature, because there's some older video we're going to look at where some English guys were saying that 20% of the geothermal energy comes from the sun, but not at 6 feet. It's all coming up from the core of the earth, pretty much. That's why you go 6 feet, because you get below frost. So that in most places, I've seen places where if it's compacted soil and it's moist, like in a roadway or something where they've dug a ditch and they've tried to put a pipe in at 10 feet or whatever, and it gets pounded and it goes to 40 below zero and it'll freeze at 10 feet. Pipe will freeze at 10 feet. Because of the moisture in the soil that conducts the cold. But kind of get started on this. No big pressure, but do get going, because it's going to take a few days. 28 readings. So if you get with 14 days roughly, and they don't have to be consecutive days. It would be nice if they were. And then your format as far as the reporting goes, we're going to talk more about that in the future. So now that you've got Topic 5 dialed up in your course and you've downloaded Google Earth, you've got Google Earth handy there. By the way, that's going to help you with your test on transformal plate tectonics, or plate tectonics in general. But let's get way out here in space for a second and take a look here. I think we're close to true north. I'm going to set this up on north here. Must have declination dialed in. I think we're at 18 degrees. Oh, there's perfect. That's pretty much right on the arrow. Should be kind of right. So if we look at the general shape Now, the Pacific Ring of Fire, correct? Coming through here. And it comes in to San Francisco into the San Andreas Fault. It might be more advantageous to look at it. Let's do this. There we go. So I went back to the USGS format. It's just a little bit more obvious and less details. Major fault convergence right here. Comes on shore in the San Francisco area, down through Southern California and into the Gulf of California here. And you can see this big shelf out here where the subduction is taking place. The suboceanic plate is subducting, going under the continental plate here in a pretty big way. And if you get back out here in space for a second, we're too far out in space. All right, let's do that. There we go. A little bit closer. You can see how this tectonic interface at the surface of the continental plate, as this oceanic plate dives under the continental plate, it's bulldozing up, and you can see the mountain ranges, how they progress inland in that same shape that you see on the coast. And then you even have a few islands out here. A couple of different theories. They think that because of this major tectonic interface right here, that there could be a collapse as this dives underneath here, that you would end up with some more offshore islands that, like you saw in Catalina. I think that's San Pedro right there. Let's see. Maybe not. It's a little further south here. Go out a little ways. Yeah, I'm pretty sure it's San Pedro and Long Beach. And there, no, this is San Pedro right here. There it is. Then you can see the offshore islands right here. Catalina. And you can see how they kind of reflect that, the bottom, the landforms in the bottom. And it's, one theory is that it's bulldozing up as it runs underneath the continental plate. This suboceanic plate is bulldozing up, forming these different landforms that you see here. And if the big one happens, like they say, this could all turn into island material here, west of the fault. And if you look at the ripples here, in the actual landform, Imperial Valley, Mojave Desert. Think of this, I'm thinking that's Lake Tahoe right there. Yeah. And then maybe Mona Lake perhaps right here. And then Death Valley. I don't think it's that far out though. That must be, that's too far out. Death Valley's right down in here, I think. So from the highest point in the continental United States, lower 49, right in here, Mount Whitney. And that's where Google Earth's kind of handy because it actually names it for you. So if we kind of zoom in on it. This must be Vegas right here. Henderson, yeah. Las Vegas. So there's Lake Mead. So Death Valley, it's got to be right out in here. California. But the landforms that we're looking at here, all the wrinkles, the way they have a kind of a symmetry. Until we get up, and this is something we'll look at in the future, we're not going to do much with it today, but until you get up into our neck of the woods, start looking at Yellowstone Lake, and you can see it right there. Yep. This is on the Snake River Rift. But what happens now is, as you look west out of Yellowstone, we saw in previous lectures the footprints of previous eruptions from the magma plume punching up through the continental crust and forming these different craters of the moon. But this rift runs transverse to what we see out on the coast. So we look at it from out in space here. It gives you a neat perspective. Most of our mountain ranges are running, you know, north-northwest to the south-southeast. And you see that then even here in get into Montana, and we get into Challis, Idaho. Some of these areas, you see that diving spot. It's in Yellowstone Lake Firehole. Let's see if we can get a picture of it real quick. Have you been there? The Firehole River? It's a pretty cool, let's see if I got a picture now. No pics. Okay. Well, it's a neat crack in the earth, you know, and let's see if it's going to show me something. Nope, it's going nuts. But then it widens out and it's slightly warm, so you've got this, you know. What's interesting about this landform is how this rift, or this Snake River rift, runs from the northeast, or east-northeast, runs along to the south, west-southwest, west-west-west-southwest. So it's more west than anything, you know. Very little bit of south in there. And then it arcs up again and goes off into Oregon. But if you start to look at these mountain ranges, let's see if we can find the Bitterroot. See if that's
There to the left.
Is that it right there?
Yeah.
Looks like it, doesn't it? Yeah, there it is right there. Whoa. Let's take a look at my house, man. Where's it at? Right down to the airport right here. I look for... Illinois Bench, which is, you know, Lake Missoula. That's a whole different story, huh?
I know where that's at.
A whole different story. Oh, there it is, way up there. Wow, that's quite the body of water, man. I didn't know it was that big. There it is. There. There's the Bow Dome, my geodesic complex out on this is Bow Lane right here.
Nice.
And then
What is that body of water right there?
it's just a 5-acre pond.
Huh.
Haven't really named it. Maybe I should, huh?
Is that a part of your property, or?
Yeah.
Nice.
And then this is an earth-coupled geodesic complex right here. So you can see that most of this here, this is the dome, the geodesic aspect. So it's an exercise in geodesic solids. We got a 2-frequency icosahedron here, 3-frequency icosahedron here. Excuse me, this is the 2-frequency, it's the kitchen area. 3-frequency, and then this is a 1-frequency icosahedron, which is just a basic 20-sided figure. And then there's the the garage, barn, greenhouse kind of thing. And that's the sleeping platform on top there. So you can sleep like 7 people head to head on top. But long story short, if we look further west out of here, the Bitterroot Valley running north and south, true to form, huh? Pretty much north to south, like you see the Imperial Valley out in California, very similar, huh? And then these mountain ranges, the Bitterroot Selway, this whole area right in here, Bitterroot National Forest, Bitterroot Selway, Frank Churchill River of No Return, the largest contingent wilderness in the lower 48. It's a lot of wild country out there.
Oh, wow.
Do you? It's nice, man. But then, as you get further west, looking for, okay, we're going to come out the end of the bottom of the Bitterroot. I wanted to see Mount Bora. Let me see if I can find that. If we get a peek at Craters of the Moon, actually, if we can get further down here, following 93 on down, if we go out just a ways, we're going to be able to see Twin Falls out here pretty quick. And the Snake River itself. Twin Falls now is located right on the Snake River Rift. Here's a bridge going across it. Let's take a look and see if this Twin Falls Tourist Center. Okay, it's not showing me the rift very well now. Just zero in on it. See, here's the, you can see where when it separates this way, looks like that bridge is kind of drooping.
After that bridge.
Looks like the bridge is drooping a little bit. Here we go. Well, they're trying to show the bridge in contact with the surface, huh? But that Salmon River Rift is separating, huh? This is where there's some big tectonics going on here. It runs all the way up then, the Snake River Rift runs all the way up. Snake River ends up going into Craters of the Moon, actually south of Craters of the Moon. And that's that tectonic, where that pluma magna was punching through the surface. Well, a point of interest here, when we were up closer to Arco, back to Arco, see if I can find it again. There it is right there. Arco Airport, so if we kind of get down closer where I can see the road here. Here's 93 coming into town, up from Twin Falls. And then you have the Spring Valley up here on the west side, and you've got Leatherman Peak and Mount Bora.
Oh, yeah.
Some gnarly mountains, man. 12, 13,000 feet. They're up there. And there's an earthquake fault from like 1985 in here. I'm pretty sure this is 93 right here, the highway, or that's the fault maybe.
You can
Let's
see it from the road.
Yeah. Well, let's see, is that, that's river there. There's this huge fault that, and when this whole earthquake happened, I think it was 1989, when this, or yeah, pretty sure it's 89, when that earthquake happened, these mountains in general grew 15 feet, and the valley dropped, you know, some 8 to 10 feet. And the pressures that were created from that earthquake, they had the springs, some, what they called valley springs, that came up for like 6-8 months of gushing water. Yeah, okay, this is the top, this is the head of the valley right here, and then here's the road coming out. it's further up in here. But the point I'm trying to make here is you see how these landforms now are northwest to south, north-northwest to south-southeast. These ridges run along here. Tall flight strip. Reflecting that, then that Snake River Rift, you can see that this is a surface maybe created by that subduction on the coast. Long time ago, huh? Formed all these wrinkles, kind of like a bulldozer. But then the actual tectonic interfaces formed the Snake River Rift, when the Snake River just runs down the crack, basically. So let's take a look at that San Andreas and some of the stuff that's going on. Another little quickie here is this arrow indicates the 39 millimeters per year of movement at this subduction zone right here. But as we come into this major geothermal area here, let's take a look. Let's get rid of that. I've lost my. So we zeroed in on the Salton Sea there, and this is kind of what's going on in that area right now. It's kind of interesting, geothermal wise. Well, but really stinky. I don't know if you've ever been there. Salton Sea. One of the theories is that could collapse and the ocean could rush in, and that could be what helps those offshore islands form that we were just talking about in California there. One potential catastrophic scenario. Here's what's going on right now. Let's get it dialed up. Oh, she's going to work. So you might think that there's heat close to the surface here because of the tectonic interface. It allows that earth temperature to come up. Got some of this in Yellowstone too, huh? But Yellowstone and likewise these are protected sites also.
Yeah, that one up there was one.
That stuff, it smells like it sounds, actually. It's the bowels of the earth.
Watch this shit splatter all over me while I'm up here taking this picture.
You see, this is salt water too, huh? Not much alive in there. Yeah, the artistic, artsy. Sweet. Little look at the mud pots there, and likewise this is available to you here in your course. Well, what did they do with that as far as geothermal is concerned?
My name is Mark Grand. I'm the Vice President of Real Estate Assets and Community Relations for Cal Energy Operating Corporation. And we're here at the Hope Plant, which is one of our geothermal plants at the southeastern shore of the Salton Sea. Well, we take hot water, or brine as they call it, and we bring it up through wells out of the ground. It's like artesian wells. We don't need pumps to pump it out of the ground. It comes naturally out. You dig it's like putting a straw in a soda though. The liquid comes out the top. That's basically how this works. And so that hot water comes up through our wells, which are about a mile down in the ground, comes up. We take that hot water and we extract the steam by depressurizing it and extract the steam. The steam is run through a turbine which generates electricity, and that's put on the line. Then the hot water that's left over from that process we clean out and we re-inject it again back into the ground to renew the resource and be able to use it again. Well, as a renewable energy, the RPS Renewable Portfolio Standard that's been put in place by the governor up to 33% by 2020, it's made renewable energy sexy, if you will, and it's put the focus on it, and so more people are looking at generating that electricity. All the utilities need to raise their standards, since we're only generating about 8% in the state right now of renewable energy. And so to raise it to 33% by 2020 is a huge task. And so that's bringing new players into the game. And geothermal energy is a base load energy. It runs 24/7. And so it's going to go hand in hand with solar and wind, whereas solar needs the sun, and it's going to...
The base load capability, that's really important as far as 24/7.
run during the daytime, and wind will generate electricity during the windy times. We run 24/7, so that's going to be the base for the transmission to get on the line and for these utilities.
It's one of the Earth's most powerful forces. So hot, almost nothing can withstand it. So volatile, it explodes from out of our planet's deepest recesses.
So who would have thought, what does Tesla have to do with Cal Energy geothermal plant or the Salton Sea, Gulf of California? It's kind of a new thing here.
Welcome back to SportsCenter. I'm Scott Van Pelt. Time now for the best available video, which comes to us tonight from...
This Tesla runs off geothermal brine. Could that be the bumper sticker of the future? And at a draw for Tesla Motors to build its gigafactory in California, says some business leaders, is the salt and mineral-rich Salton Sea in the Southern California desert. A company has recently developed game-changing technology to produce lithium from geothermal brine, a leftover of geothermal energy production at the Salton Sea, the state's largest lake. Tesla is considering sites in 5 states, Arizona, California, Nevada, New Mexico, and Texas, for its so-called gigafactory that would produce lithium-ion batteries for its electric cars.
Yep, the salts left over, the byproducts which were considered, the hazardous waste. So an unexpected plus. But there's some other things that happen with salts.
Okay, so here I am. This is a blown well at a geothermal plant that is not owned by Cal Energy. But I was at a meeting for the renewable energy thing for the county for their master plan. There is no way to notify the public if one of these blows like this. And that is CO2 supposedly going into the atmosphere. I'll post this when I get home, but you can smell this stuff. It is horrid. It is horrific.
Well, one aspect of, no carbon footprint. Well, not always so, huh? Things like this happen.
I'm going to get back in my car and drive. But this is what we're looking at around the Salton Sea. They want to put geothermal all around the southern end. But what if one of these blows? So that's the question I'd ask the county and the state and the feds and all the people who want to dip their pocket in here and make some money is, what if this happens all the time? What do we do then? You want your kid breathing this in? Do you want to breathe this in? Do you want to spend time in the hospital? You need the right people. You need to get involved. You need to show up at the next meeting that these people put on May 20th in Salton City at the Salton Community Services District. You gotta do it, guys. This is crazy. We need answers. They don't need to have deep pockets. They don't need to have any more profit. We need to know if we can live here anymore. Bye.
Well, there's a backstop preventer, blow-up preventer devices that they've developed since that was probably back in early 2000s.
Well, it's not nearly as nasty as some of the stuff that's coming out of fracking wells.
Yeah, well, and the comment was it's not nearly as nasty as what's coming out of some of the fracking wells, which is correct. That's one thing we're going to talk about too, is the process of fracking, the actual mechanical process. I think that's, we get up to around unit 10 or something like that. But the whole idea is one of the top secret fracking fluids is going to blow your mind. Now let's take a look here at some other California geothermal.
This is what really the United States is all about. Americans say,
see, I got to cue those for that. So Calistoga, this is a large area. There's lots of different geothermal sites. It's up just slightly northeast of San Francisco. You see, that's the evaporator, or that's the cooling side of the turbine, huh? So for turbine efficiency, hot coming in, cold going out. As things expand to physics, you get cooler. So you can see all the surface pipes. These are production wells down here. And then you can actually see probably over the top here that you're not seeing well, your turbine's got to be sitting in here someplace. That's the cooling stack. So the turbine's probably up underneath this tower perhaps.
Welcome to one of Cal Energy's geothermal power plants. Unlike other power plants that rely on coal or other fossil fuels to create electricity for homes and businesses, geothermal power plants use superheated fluids from the Earth's geothermal resources to generate electricity. The natural heat of the Earth creates geothermal resources. This heat comes from molten rock called magma, located at the Earth's core, deep below the geothermal resource. Over thousands of years, rainwater seeps through cracks in the Earth's surface and collects in underground reservoirs. The magma heats the water until it becomes a superheated fluid. To reach the superheated fluid, wells are drilled 5,000 to 10,000 feet below the surface of the Earth. These wells, called production wells, bring the superheated fluid to the Earth's surface, where it can be used to generate electricity for homes and businesses. This geothermal power plant uses crystallizer reactor clarifier technology, a process that turns the geothermal superheated fluid into steam while removing solids from it. The steam is used to drive a turbine and generate electricity. All remaining geothermal fluids are injected back into the reservoir for reuse.
And this is some of the byproducts that we were seeing from Salton Sea that Tesla's after. Not so much in this area, but there are some other byproducts that they're finding. Some simple things like gold, silver, other precious metals.
Under its own pressure, superheated fluid from the geothermal resource flows naturally to the surface through production wells. As the liquid flows toward the surface, the pressure decreases, causing a small portion of the fluid still within the well to separate or flash into steam. At the surface, the superheated fluid and steam mixture flows through surface pipelines and into a wellhead separator. Inside the separator, the pressure of the superheated fluid is reduced. This causes a large amount of the superheated fluid to rapidly vaporize and flash into high-pressure steam. The geothermal fluid that is not flashed into steam in the wellhead separator flows to a second vessel called a standard pressure crystallizer, where an additional amount of standard pressure steam is produced. The flash process continues in the low pressure crystallizer. The remaining fluid is again flashed, this time at a lower pressure to produce low pressure steam. All of the low pressure, standard pressure, and high pressure steam is delivered to a turbine. The fluid that is not flashed into steam flows into the reactor clarifier system and is then returned to the geothermal reservoir through injection wells.
This is the issue with the reinjection, where the environmentalists are concerned about, what's going to happen, over a period of years. But some of the wells that have been in production now for 20 years with this technique have shown no obsolescence. Their production has increased.
Turbines are the primary piece of equipment used to transform geothermal energy into mechanical energy. Pressurized steam created from the geothermal superheated fluid flows through pipelines to large steam turbines. The force and energy in the steam is used to spin the turbine blades. The turbines turn a shaft directly connected to an electrical generator. An electrical charge is created when magnets rotate within the generator.
So one of the downsides here, as far as the steam being applied directly to the turbine, there's still some,
the turbines turn a shaft directly connected to an electrical generator. An electrical charge is created when magnets rotate within the generator. Large copper bars carry the electrical charge to a step-up transformer outside the plant. Within the transformer, the voltage is increased before the power is sent to the power lines that carry it to homes and businesses. Geothermal energy is a sustainable resource because with proper management, a geothermal resource can remain a renewable source of energy. Water trapped deep within the earth will naturally replace the superheated fluid that is drawn from the geothermal resource through surface wells. However, it is possible to deplete the geothermal resource by removing fluid faster than it can be naturally replaced. To help prevent this, the steam used in the geothermal power plant passes through a condenser that turns it back into fluid. At this stage, it's possible to recover minerals from the geothermal fluid before it's injected back into the earth.
See, and this is they're actually finding that this is one of the big pluses because they're getting a fair amount of gold and silver and precious metals, other lower grade precious metals. And this also, being a closed system this way, it kind of takes the pollution aspect out. When you start dumping the steam into the air, it might have a little sulfur smell to it. And the sulfur itself is good for different purposes. So
this condensed fluid, along with the fluid that did not flash to steam, is injected back into the underground reservoir. Magma naturally reheats the fluid so it can be used again.